Good morning, everyone. I'm Hyungjun. I'm going to talk about compiler-assisted code randomization. This is a joint work including my advisor, Mihalis Polikonekis from Stony Brook University, Yawei Chen and Long Lu from Northeastern University, and Vasilis Komaris from Brown University. Let me start by the need for fine-grained code randomization. With the introduction of memory protection policy that does not allow both writable and executable permission in memory, attack paradigm has shifted from code injection to code reuse or return-oriented programming. Address space layout randomization has been introduced and has been deployed by modern operating system, but it does not provide sufficient mitigation. It is defeated by information leaks. It's because relative distances between functions and basic blocks are maintained. That's why we need fine-grained code randomization. It makes gadget locations unpredictable. Here, gadget is a sequence of instructions for constructing a functional payload for attackers. We have the advanced just-in-time ROP exploitation technique that allows attackers to collect the gadgets on the fly, which ended up bypassing fine-grained code randomization. But still, we have another protection mechanism called execute-only memory. Execute-only memory also relies on fine-grained code randomization to be effective. To make a long story short, we need fine-grained code randomization for two reasons. First, ASLR is insufficient. Second, execute-only memory also requires code randomization as a prerequisite. Decades of research have shown its effectiveness of code randomization, but it has not widely adopted yet until today by any software vendor. Code randomization technique from the prior works can be done by either end users or software vendors. End user can recompile the source code, or they could rewrite the binary with a static analysis or dynamic analysis. But in both cases, they are responsible for performing a complex and cumbersome process. Software vendors also can deliver randomized variants to each user through app stores. But if you think about any software that is used by tens of millions of users like web browsers, it would be very costly to generate and distribute the randomized copies. We have thoroughly thought about key factors for making code randomization practical. So first factor is transparency. That is, software distribution and installation should remain the same. And the second key factor is reliability. Binary rewriting requires ultimate precision. It involves a highly destructive process. So there are two different techniques for binary rewriting, which is static rewriting and dynamic rewriting. And static rewriting suffers from correctness, mostly because of indirect transfers and thus incomplete code coverage. And we have dynamic rewriting, but it also suffers from performance degradation and compatibility issues. The last but not the least factor is compatibility. The randomized binary should be compatible with the existing software operations, like crash reporting, code signing, patching, and updating, and also a variety of code constructs that includes shared object, exception handling, compiler optimizations, and position-independent code, and so forth. Here is the comparison table that shows the needed information for binary rewriting from prior works. Some of the works requires a source code itself for binary rewriting, and some works requires disassembly, relocation, or symbol, and so forth. The self-rando on the bottom is the closest work with ours. They used the relocation and function boundary, and they stored it as a metadata into the executable. We'll get to that later on. And there is a paper that systematically studied the prior works on automated software diversity, which was presented Auckland in 2014. It concluded, we pointed out several promising directions. There is currently a lack of research on hybrid approaches, combining aspects of compilation and binary rewriting. So this is exactly what we did. So we have set up the research question with the following goal. Can we reliably randomize binaries in a transparent way compatible with existing software? So here is an overview of compiler-assisted code randomization. Our approach is based on compiler-rewriter cooperation. So first, compiler takes the source code and it is transformed to intermediate representation, and then assembler takes intermediate representation into the code as an object file. At this point, we collect the supplementary information from the compiler as metadata, and then object file combines those object files into the final executable. We used compiler, LLVM as compiler, and Gold as linker. Once software vendor is ready for distributing the master binary, and it is transferred to the end user over legacy channel. And then the end user triggers the rewriter to produce randomized binary. Let's have a look at transformation assisting metadata now. The most important thing is that we have to identify the object boundaries for transformation. If you see the code in the executable, the code consists of multiple objects, and each object consists of multiple functions, and then each function consists of multiple basic blocks. Before moving on, let me briefly mention code generation in LLVM backend. So it has an internal hierarchical structure called machine code framework that consists of machine function, machine basic block, and machine instruction. You can think of these three components as just a function, basic block, and instruction. And you see here the machine instruction number 3, which is colored in orange. This represents branch instructions. We also have the nope colored in gray. This represents the nope code. Once this structure is complete, then machine code assembler treats the code as a series of fragments that are data relaxable and alignment fragments. At this point, assembler does not have any high-level structure like a machine function or a machine basic block. So we label the parent machine basic block and machine function per each machine instruction. So for example, here, machine instruction number 1, 2, and 3 belongs to basic block number 1 and function number 1. So that's why we label them as machine function number 1 underbar and BB number 1. And as the layout is being determined, there is an internal function called emit instruction that decides both machine basic block and machine function sizes. Here, the first instruction is 5 bytes in size. The second one is 3 bytes in size. And these are combined together which forms a data fragment. And when assembler encounters the branch instruction, it forms relaxable fragments. If you think about the instruction of the jump instructions, there is the operand. Sometimes this operand should be expanded. If that's the 1 byte, then the target is not reachable, so it should be expanded to 4 bytes. That's what the instruction relaxation does. So here we have the 5 bytes for relaxable fragment. And the last one we have to see is no bytes. No bytes is formed as alignment of fragments. Once all the layout is determined, then we store this information into the metadata in the object file. Let me, another important metadata that I'd like to mention is the fix-up information. You see there are 2 different byte codes, one on the left from object file and the other one from finally executable on the right. And there are instructions in the middle. Here, the jump instruction has the fix-up, which is D in hex, pointing to some base block, but this fix-up has been already reserved at compilation time. But if you see the call instruction, which is sum function, the sum function is not defined inside the object file, so it produces the relocation entry in a relocation table for an object file. So there are 3 different kinds of fix-ups we have. It could be reserved at compilation time, link time, and load time. But if you see the fix-ups either at link time or load time, you might find the relocations in the relocation table, but most of the fix-ups that was reserved at compilation time was missing. So I just defined that these 3 different categories as 3 different sets as A, B, and C. Then the set A would be the superset that includes the entire fix-up. So we are collecting this information, including offset from section base, dereferencing size, and the value that is either absolute or relative. So here is the table that summarizes the metadata. We have talked about layout, base block, and fix-up. So another thing that I'd like to point out is jump table. Actually, jump table, the fix-up information has the corresponding jump table information. That includes the size of each jump table entry and the number of jump table entries that could be collected at compilation time. So once everything is done at compilation, then linker consolidates per object metadata. So linker plays 3 different roles, which are first constructing the final layout and reserving symbols and updating relocation information. Here we have added another feature, which is merging, adjusting collected metadata from each object file. So this metadata update includes layout, page block size, and fix-up offset. So once everything is done, master binary is ready, then the end user is going to rewrite the binary at installation time by parsing integrated metadata. So here, recall that we don't do any disassembly or binary analysis at this phase. We reconstruct the layout from the base block, function, and object from bottom-up level, and then we reconstructed the binary hierarchy as a tree structure. And then we perform randomization on that, and then we rewrite binary. The 3 boxes on the left shows the sections in ELF to be updated for fix-up information, symbol information, and exception handling. We have evaluated our prototype using 20 binaries from Spec 2006 benchmark. And we have generated 20 different variants per each binary. And we got the runtime overhead on average with 0.28%. And we have a moderate file size increase with 11%, 0.5%, 11.5%. So there are a lot of topics that we have not covered. So we have a lot of challenges for enabling robust and practical transformation. So we have not talked about how to support for various software constructs, including exception handling, inline assembly, linking time optimization, and even control flow integrity. We have several randomization constraints, and we also had some implementation pitfalls and some current limitations. But I think most of the limitations can be resolved with the extra effort, engineering efforts. If you're interested, please read our paper. To wrap up, I have presented the compiler-assisted code randomization at both function and basic block level. We have facilitated our prototype by transformation assisting metadata stored within augmented executables in a transparent, reliable, and a compatible way. We have also successfully integrated with our prototype with the popular package manager APT in Linux. We are open sourcing our prototype in this link. The code is now available if you are interested. Thank you very much for your attention.
All right, we have a few minutes for questions. Is it delayed? Ah, there we go.
Hi, excellent talk. Matt Van Gundy from Cisco. Can you talk a little bit on your choice of installation time randomization as opposed to, say, like load time?
We selected the installation time. You can do it at the randomization at load time as well, but if there are a lot of fixed up information, say more than hundreds of thousands, then maybe it incurs the the randomization time. It increases a lot. I mean, it's mostly a few seconds, but sometimes a minute. Then the end user will not be tolerable for that. So we chose the installation time. And the other thing I'd like to notice is we use the Python script, so that's why the randomization process is a little slow. So if you use the C or C++, then we could increase the randomization and installation time more, and maybe we can do it at load time as well.
Thanks.
Let's go to that side of the room, I guess.
You have built the talk was very interesting, thank you. And the way in which you've been doing things is also fairly interesting. You built the transformation
Yes.
using the ELF framework, and I presume you're plugging into Vellum. Have you done anything to actually prove your transformations correct?
Yes. If the transformation has not been correct, then we could not even run the 20 binaries from spec 2006. We have tested a lot of other executable as well, and because we do not have the extensive test cases, so we don't know. I cannot guarantee that everything was fine, but we did not have any problems that we had encountered so far.
So you validated with tests, but you've not verified with proof.
So if you have the executable, then it's kind of hard to verify your executable is fully functional because mostly
your method of transformation.
Wait.
verified your method of transformation preserves semantics.
Maybe check
Yes.
this offline.
I should stop.
Yeah,
Yes, please.
sorry. We're actually out of time, but the rest of you can maybe talk to him after, at lunch. So let's thank him again.